Gotta make sure that my like volcanology say field trip is not at the same time.
All right, so we're gonna finish up some stuff from last time. We're talking about marine sedimentation with respect to the carbon cycle. We talked about organic carbon, we talked about inorganic carbon, we talked about in the average in the oceans, the following particulate matter has a ratio of organic to inorganic stuff of 4:1. A lot more living, or not living, but used to be living organic tissues than there is shell. That goes into our understanding of the balance of carbon import and export in the ocean. So, and then we started talking, I think I left off on this slide, about calcium carbonate deposition on the seafloor. In a way, calcium carbonate deposition is a reflection of how much production is happening in the surface ocean, secondarily by how soluble calcium carbonate is. As we talked about, both forms of calcium carbonate, calcite and aragonite, both get more soluble as it goes down in the ocean. So we find the equivalent of what's called the snow line, which we talked about last time, the carbonate compensation depth is different between calcite and aragonite. The aragonite has a shallower depth and it's easier to dissolve. But, and I mentioned the analogy of snow falling on the ground last time, even and staying on the ground, even when the temperature is above zero. In essence, if you have a high supply of shells raining down on the seabed, you've got high biological productivity. I think specifically about the upwelling zones we were talking about last time, then it can overwhelm the rate of dissolution and it can still accumulate on the seabed. So that when we look on the seabed and we look back in time, in geologic time, and they're recorded in sediments, where we do and don't see calcium carbonate is as much a reflection of how much supply was there as it is of the depth where it ended up settling. Plus, in addition to being sort of absolutely dissolved or not, the calcium carbonate shell can also experience various changes in between that, partial dissolution, loss of ornamentation, recrystallization, etc., which people can look in at under a microscope at the shells and the sediment, and then be able to approach more understanding of this omega horizon, which is a place in the oceans where we're right at saturation for calcium carbonate, which is just a function of pressure and temperature. Okay, and we talked about omega last time, so you can look back if you want a reminder of that. So the compensation depth that you've learned about before is a kinetic horizon primarily. It's a sort of a what is the rate of supply and the rate of dissolution and how do they balance. We can do better than this to reconstruct the structure of the water masses with respect to how corrosive they are or are not to calcium carbonate. Does anyone remember something we talked about last time that happens to the ocean as the seawaters and makes its transit from the Atlantic to the Indian to the Pacific in the deep water masses and would make it more corrosive to calcium carbonate? I think respiration, CO2, acid. So the deep water masses in the Pacific Ocean are slightly less basic or slightly more acidic, even though they're still at a basic pH, because of all that accumulated effect of respiration of infalling organic. That makes that water be able to dissolve calcium carbonate a little bit better. So at the equivalent depth in the Atlantic and the Pacific Oceans, you're going to see more corroded shells on the seabed. Okay. So we can divide up the types of sediments we look at into various categories. There's all sorts of categories here, and you can go species specific and everything else, but the three primary categories of carbonate sediment that people look at in different areas to try and get a handle on this difference between the kinetics and the chemical equilibrium that we're actually after learning about is foraminiferal ooze. This is sand-sized calcite grains from foraminifera, which are a kind of organism that live both in the upper water column, we call those planktonic foraminifera, and ones that live on or near the seabed, we call those benthic foraminifera. Now, normally, people will look at the planktonic species because they record something about surface conditions and the sort of falling of particles to the ocean for this particular application. Nanofossil ooze, these are other kinds of calcium carbonate, calcite fossils, but as the name implies, nanofossil. These are small organisms, smaller shells, easier and faster to dissolve. And one of the most common forms of organisms that make them are called coccoliths. The third kind of sediment we look at are pteropods oozes. The reason we look at pteropods is because pteropods make aragonite. So they're coarse like the calcite foraminiferal ooze, but this is other form of calcium carbonate that dissolves more easily. Okay? And so when you look on the seabed, this is a depiction of a sloping seabed, a population of organisms living up in the upper water column. And you could consider it those same three things that I said. You could say, all right, you know, the black dots are foraminifera calcium carbonate. The you know, open symbols are coccoliths, and the slash symbols are pteropods. Okay, and so you get at some point to a depth in the ocean where you're below the compensation depth, right, where everything essentially dissolves. It's never 100% everything. You'll find the occasional shell as is shown here. But there are other horizons shallower than that where we start to see changes in the shells. One of the common ones you will see referred to in the geological literature is something called the lysocline. And the lysocline is the place in sediments. If you go all around the oceans today, the Pacific Ocean, you took surface sediments, and you went to the Atlantic Ocean, everywhere else, and you looked at what shells were present, and you plotted that up as a function of the depth of where I collected them from. The lysocline is essentially the place where we start to see a significant change in the population reflected on the seabed of shells relative to what we know is above it. So let's say you did a plankton tow up here, and someone went through and looked at all the species and counted them up and said, yeah, we got so many coccoliths, so many pteropods, so many forams. And they look down here and they see a different proportion. So this is one horizon that basically says, yeah, once we start to see statistically significant difference in the population of shells here relative to what's up here, then we know we've had some dissolution or some other preservation feature. And so therefore, you know, that's an impact of the water masses and the particular water masses in that particular ocean basin at that particular depth. And this horizon moves around, right? Like, so if you are underneath one of these upwelling zones where there's a very high supply of shells, the lysocline may be depressed and you go deeper down in the ocean than if you're in a place where there isn't a lot of biological productivity. Can anyone think of a place, we talked about it last time, in the oceans, in the surface water, where there isn't very much going on in the surface water in terms of biological productivity, photosynthesis, phytoplankton?
Isn't it like the gyres or something?
Totally, the centers of the gyres. And so if we go into the North Pacific, which is a very deep ocean basin, we all around us here, we go to that gyre, we collect surface sediments, we're looking like this. So that's not the only horizon. There are other horizons too that we can identify. And so one of them, some people have done these experiments. This is one sort of classic one described here, where they took a bunch of sort of like bowling ball sized perfect spheres of calcite and put them on a mooring and left them in the ocean for some period of time. And they weighed them beforehand and they were all the same weight and blah, blah, blah. And then they came back later and pulled the whole thing up, dried them out and weighed them. And then this is what they see, how much weight was lost. And you can see as you come down, you know, there's no weight loss and there's like a slight bump up, you know, here in the mid-water depth. But in this particular location and around 3,500 meter water depth, we start to see this big excursion. Now this is shallower than the CCD, but this is where we start to see, yeah, we're really starting to see dissolution. So it turns out, and I didn't really mention this previously, but not only is the way in which stuff dissolves a function of supply, which we've kind of mitigated here by just putting the balls in place, but there also happens to be the kinetics of dissolution of calcium carbonate are also pressure and temperature dependent. So that the more undersaturated the water is, the easier it is to dissolve calcium carbonate in terms of the speed and the pace. So this is some other level, okay? And some people call this level the R0 level. I don't know where these names came from. You know, they're from various researchers, and a lot of these were defined in the 70s, 60s, and 70s, where maybe there wasn't as much communication between stuff. But so in this particular location, we've got this R0 level, and right below that, we have the lysocline, and then the CCD is somewhere around 4.7. And so you can see this about a kilometer-ish difference between those depths. Okay, so now here's another thing to think about as we're piecing together, trying to reconstruct the carbon cycle from shells on the seabed, is that the seabed isn't flat, right? For instance, we know we got mid-ocean ridges that run up, in some cases, the middle of the ocean basins, in some cases, one or another side, but they represent topographic highs. We also have seamounts, right? That also represent topographic highs. So that if all other things being equal, the supply of shells is the same everywhere in a certain part of the ocean basin, but the seabed changes its depth, then we're going to see different shells recorded in the sediments there as a function of primarily the depth and the rate of dissolution. However, if you also now take that bit of plate and you move it along so that as in time, as we go down in the sediments, they're recording the different depth of seabed, right? We know that when ocean crust is first formed at mid-ocean ridges, it's hot and it's shallow. And it starts to cool over time and it sinks. And there's a square root of T relationship for that, that as that happens, the seabed starts to sink. And so as it sinks, it will go through different transitions, if it's happening to go through the right depth range, where pteropods, the aragonitic material, will or won't be present. And then Globigerina is a type of foraminifera. They will or won't be present. And then we get below the CCD and no shells are preserved anymore. And we have clays, which are sometimes called red clay. That's kind of an old fashioned term, but if you go anywhere in the oceans today, away from the coastlines where we have a lot of terrigenous sediment, and we're deeper than where calcium carbonate can be preserved, the primary form of sediment is clay. And it's different in the different parts of the ocean basins, partly because of what's in the rocks around the ocean basin. Most of this clay is provided through dust deposition, not through water flowing in on the side, but small particles moving aloft. We get clay particles and other metamorphic mineral grains deposited here in Hawaii that come from the kind of global weather circulation patterns that are primarily sourced from the Himalayas. And they end up being an important source of some metals in our soils. But so in any event, you can see here in detail, you know, what they would call a clay doesn't have zero calcium carbonate. It's got some in it, right? So these are terms that refer to what is the dominant thing in a sediment. It's a Globigerina ooze, if at least 2/3 of it is calcium carbonate from foraminifers, okay? Globigerina just happens to be a very common species that we find in all of the ocean basins. And this is the relative proportion of calcium carbonate that we see in those sediments. So you can imagine going and reconstructing through drill hole, like has been done in the what's now called IODP, used to be called ODP, Ocean Drilling Program. Before that, it was called DSCP, Deep Sea Drilling Program. They got holes all over the ocean basins that we know where they are today. We can reconstruct in time how plates were moving, and they can look at variations in sediment pattern and then basically infer two things: what was happening in the upper water column and what is happening with the seabed depth as it moves along. Okay, and so a consequence of all these things that we've talked about now is that when we do depth reconstructions for the various ocean basins, another thing I should point out about depth reconstructions in sediments is that surface sediments tell us about the depth today, but when we look down into the past in the sediments, not only is the seabed sinking because it's cooling, we also have compaction as we put more and more sediment on top of it. So there's a lot of calculations people have to do to kind of uncompact sediments when you go back in time. But it can be done. What we find on average is that this is the kind of amount of calcium carbonate as a percentage in sediments in the Pacific Ocean and in the Atlantic Ocean. And we see more calcium carbonate at deeper depth, which makes sense with all the stuff we've been seeing, because the deep Atlantic Ocean waters are younger, less respiration, less acid, less corrosive to calcium carbonate. Does that make sense to everyone? Okay. So you might say, well, okay, that's the current configuration of the ocean basins. What was it like before we had an Isthmus of Panama, for instance, where we had communication of seawater between those two ocean basins in Central America? And that changed about 25 million years ago. Or what was it like when we didn't have as big of an Atlantic Ocean, or we didn't have any Atlantic Ocean? And in some of those cases, as we go deeper and deeper into the geologic past, We can no longer look at marine sediments in the ocean basins. We got to find them preserved, you know, in the rock record on continents. Sometimes that's a lot more difficult to reconstruct in a volumetric sense, but people do these kinds of studies all the time to try and look at how that basin to basin fractionation that we talked about last time, the fundamental difference between the Atlantic and the Pacific, might have varied in time into the past. So this is kind of a summary of how geographic variations in calcium carbonate preservation reflect a whole bunch of different stuff, such as this compensation horizon that, you know, whatever horizon it is, whether it's the calcium carbonate, calcite compensation depth, the aragonite compensation depth, or one of these shallower things like the lysocline or the R0 horizon, they all get shallower as the water mass gets older, right? And older in this context just means when was the last time it was in contact with the atmosphere, okay? There's also an impact for what is the depth of the seabed. And finally, there's an impact of what's happening in the upper water column, right? And so as you imagine, we talked about last time, we've got these circulation patterns in the oceans that cause us to have much higher biological productivity in our coastal upwelling zones and our equatorial upwelling zones. Those are places where there's way more stuff living in the water, like a factor of 10 to 100. So there's way more shells falling out. So all other things being equal, if we go underneath those parts of the ocean, we're going to find a much deeper accumulation depth because there's a much higher supply. And so I understand it's like a lot of moving pieces here, but this is how people basically go back and try to reconstruct what was the carbon cycle like at different periods of time in the past on the basis of what we find in the shells. Because the organic matter is unreliable. Some of it decomposes either as it's falling or later, but the shells are a little bit more straightforward. So recall that example I gave you last time about how the total organic carbon preservation on the seabed increases during the last glacial maximum compared to today, right? That's because we had less of this circulation variation during the last glacial maximum because most of the North Atlantic was iced over. And so that meant that we could preserve more organic matter. So that's one way to look at it. But in those same sediments, people can also look at the shells and look at how they vary over that same sort of time frame and change of conditions, and then extrapolate further back into the past, to periods of time where we can't compare organic matter and organic matter as reliably, which the deeper we go in the sediments, the less reliable that intercomparison goes, and say something about how this may have changed either globally or regionally or even locally. Okay. So for instance, here's just an example of how the CCD deepens as we go from one place to another, which is, you know, basically subtropical and then sort of total supply and in the equatorial regions where we have that upwelling, countercurrent upwelling, and we can see that the horizon gets deeper, right? And that's a supply thing. This is a calculation of dissolution rate, just using the kind of understanding of the kinetics and the equilibrium and that omega factor by measuring the water itself. And we always see the rate of dissolution, actual dissolution, lagging behind this hypothetical one. But the higher the supply, the deeper we push those directions. Okay, so if you now say, all right, well, let's look through the ocean basins. Let's do a north-south line through the Atlantic Ocean, the youngest deep water masses on the planet. And we go a transect from north to south on the west side of the ocean and the east side of the ocean. Can anyone remember something I said that happens on the east sides of oceans last time? Eastern boundary currents, yeah?
Because of the Coriolis effect, you get that welling on the eastern.
Right, you get it on all the coastlines, but you get more on the east side. Just tends to be more intense on the eastern. That's why the California current, for instance, the Humboldt current. So we see slightly different things in the east than we see in the west. But the key thing you'll see here is that this omega, this theoretical, what's the depth at which calcium carbonate is going to start to dissolve, right? That's relatively flat through the oceans as we go north to south. There's a slight, we get into the northern hemisphere, this starts to get a little bit shallower because the supply of more organic rain, calcium carbonate particulate goes down a little bit. But then we see these other horizons the R0 horizon, the first kind of indication of dissolution, the lysocline, where we start to see significant change in weight in those balls of calcium carbonate, and the CCD, they're layered, and they're layered the same in both cases, but there's slight differences. For instance, under the kind of upwelling zones that we find off of, it's actually not so much upwelling as there's more upwelling in the east, I should say, than in the west. And so we see that kind of diminishment in the southern hemisphere of upwelling gives us less supply of shells. And so all these horizons kind of come up and approach each other. They get closer together. The farther apart these horizons are, probably is largely from geographic variations as a function of the supply. Okay? And something that shows up really well on the west, better than in the east, is we have at the equator like sort of a shallowing, and this is related to upwelling, not so much upwelling in terms of the supply, but upwelling in terms of what it does to the corrosiveness of water in a relatively sort of mid-water depths, right? And that helps to make the seabed a little, or sea water a little bit more corrosive. So one other thing to think about, you know, in addition to sort of circulation and what's happening on the seabed from supply, from surface waters and a depth, is to think about how does this then relate as well to the movement of oceanic lithospheric plates. That's not going to affect what's in the surface sediments, but that will affect what's recorded in a stack of sediments in any place over time. So think about, go back 50 million years ago, and you're at the mid-Atlantic ridge, and you're making some crust, and that stuff starts slowly moving along and getting deeper, and getting a supply of particles falling on it. It makes a stack of sediments, and you can go and look through that and see variations in those sediments that track a combination of things. They track how that piece of plate has moved through the ocean, reflecting differences of in the upper water column, and what's happened to that seabed as it's gotten older and deeper, right? Which exposes the surface sediments to more and more corrosive water. So this is a graphic that tries to illustrate this concept of plate stratigraphy, which is a way of going back and looking at a whole bunch of different stacks of sediments over the same time interval, over a large geographic region like the North Pacific Ocean or something like that, and trying to put it into context of the fact that, you know, what we see happening with deposition. So when you're right at a submarine volcano, whether it's a spreading center or something like Loihi, which is now renamed Kanaloa, you sometimes find sediments that are rich in iron and manganese because the geothermal fluids that come out have reduced iron and manganese. They touch seawater, that stuff oxidizes and precipitates. But once you get any kind of distance away, a kilometer or so, you don't really have that stuff anymore. And if it's shallow enough, you'll deposit calcium carbonate, right? And if you're talking about a mid-ocean ridge where it's producing crust and that crust is moving along, at some point the crust is going to age and cool and dip below the saturation horizon, and you won't preserve calcium carbonate anymore. So you only preserve that red clay. But this carbonate from below it, that from when the crust was over here, it's still there, right? That stuff which has moved along. So we see a sequence in the sediments. And this is an example from a part of the Eastern Pacific where the East Pacific rise, which runs, you know, comes out of the Gulf of California, and then it runs down, you know, next to Mexico, offshore, obviously, and then it continues kind of further off into the ocean, all the way down into the southern hemisphere, and it's spreading at kind of an angle. And this is what, you know, gives us the alignment of the Hawaiian Islands as they're built along on that crust that was formed there 65, 70 million years ago. But on the way for that crust to get here, it cools and receives different sediments. It also, if we start in the southern hemisphere of the East Pacific rise, and we allow that crust to form and then start to move north, it will go under that equatorial upwelling zone and get a pulse of additional sedimentation. So we'll start to see, you know, conditions where we have calcium carbonate because the crust was shallow, and then we don't because it got deep, and then all of a sudden it went under the equatorial upwelling zone, and we start to see calcium carbonate again. If that makes sense, right? Hopefully that makes sense. We can also look at other things too, right? Remember we talked about the supply of siliceous shells last time. These are more complicated because they're the upper water columns are corrosive to them. But when we do see the supply of diatoms or radiolaria preserved in the sediments, that usually tells us that there's a very high supply in the upper water column. enough to preserve some of it. So I realize there's a lot of overlap here between the kind of geology, the biology, at least in terms of the ecology and the chemistry. But this is sort of how the real world of how we try to reconstruct what did the carbon cycle look like, the marine carbon cycle look like in the past. And this is our primary archive. All right, so this just describes what I just said. So if you want to read it in more detail, then you have it there. Okay, so now before we get on to today's thing, there's just one question that came up yesterday, so I just want to make sure everyone knows this, that, what is ECS, right? You need it for one of the homework problems. And we talked about it in, I guess, twice. We talked about when we talked about soils, when we first talked about cation exchange. But I just kind of want to emphasize that CEC, cation exchange, is a property of the solvent. It tells you how much charge imbalance is there on a solid that can be neutralized by stuff coming from solution and sticking onto it, right? And that doesn't really change unless you change the solid somehow. But the ions that make up the CEC can change. We talk about this example of taking a terrestrial clay and sticking it in seawater and looking at the populations change. So when we look at the population of individual ions, which is what you have in the homework problem, each ion, potassium and calcium and magnesium, we refer to the amount that's actually there of that particular ion as its ECS. So it's kind of like a CEC, it's got the same units, milliequivalents per 100 grams. If you add up all the ECSs of each kind of ion, magnesium, potassium, hydrogen, or whatever, they should sum up to be the CEC. All right. So now we're going to get on to today. We're still talking about the marine carbon cycle, so it's not that much of a segue. But what we're focusing on now for today is how do we use stable isotopes, primarily of oxygen, but secondarily of carbon and hydrogen, to tell us something else about how the climate system on the planet was working, which we can combine with the kinds of calcium carbonate and carbon cycle preservation stuff that we just finished talking about to get a fuller understanding of climate history on the planet. Right? And so next time, today we're going to talk about stable isotopes. Next time we'll talk about what we call paleoclimate records, which is putting together the stuff that we've just been talking about. And then we'll have a brief summary of how this informs our predictions with respect to greenhouse warming. Because pretty much everything that people are saying about the rate at which things will happen, the timing, the location, is based on our understanding of the past, reconstruction of the past, uniform material. All right, so these are some simple aspects about isotopes. Everyone knows what an isotope is. I just want to make sure that there's no, okay. So because isotopes have different masses, even though they have exactly the same chemistry from a valence electron perspective, if you're in a water molecule, it can have some hydrogen, which has got 1 proton in the nucleus, and some deuterium, which has got 2 protons in the nucleus. Chemically, the bond between hydrogen and oxygen doesn't really care about the mass of the nucleus. Okay? Same thing for oxygen. Oxygen comes in a flavor, oxygen 16, also comes in a flavor called oxygen 18. A third flavor called oxygen 17, which is much less abundant. But the chemistry, the valence electrons of that bonding interaction doesn't change that much. However, there are still processes that can separate out the chemicals as a function of what the isotopes are because of the mass. And we're going to talk about 2 main processes today. And these are defined as something called isotope fractionation. Fractionation is just a process of separating one isotope from another and making a measurable thing, okay, that we can detect in different pools of material. And these variations in the largest extent can get up to a few percent, right? We have isotope fractionations in some systems. As you can imagine, the heavier the element, then the less fractional difference there is between masses, right? So if we go to really heavy elements like uranium, there is isotope fractionation. It's much harder to measure, but instead of being, a few percent or even a few hundredths of a percent, they can be in like the parts per million or tenths of parts per million. So we're going to focus on the traditional isotope fractionation that people first started studying back in the 40s and 50s when mass spectrometers were first invented for carbon, oxygen, and hydrogen. And those end up being the kind of most practical for understanding the carbon cycle. There are other fractionation systems that people have applied, nitrogen, sulfur, some transition metals that are also really useful for various things. I don't want to slight them. We just don't have time to talk about everything in the class, and we're going to focus on carbon, hydrogen, and oxygen. So this is a table of the isotopes that we commonly have of those three elements. So for hydrogen, and I want you to kind of pay attention to the notation here, the atomic number is usually written below at the lower side. Sometimes you see it on the left, sometimes you'll see it on the right. But all these three forms of hydrogen have one proton in the nucleus. That's the atomic number. But the atomic mass is different, right? Which causes them to fractionate differently. Now, hydrogen and deuterium are long-lived, non-radioactive isotopes. There's a third isotope called tritium, which is radioactive. It's produced on a planet and it decays all the time. And so there's a certain amount of it. It's much smaller. And for this discussion, we're not going to really worry about it. For carbon, there's also three isotopes that we have. Two of them are stable, carbon 12 and carbon 13. There's a third one, carbon 14, which you've all heard of, which is also radioactive, produced in the upper atmosphere. And for this discussion, we're also going to ignore that. But everything that we're going to talk about with respect to carbon 12, carbon 13 fractionation applies when you're doing radiocarbon dating. When that material gets formed, there's a fractionation of 14 from 12, and we have to account for it. It's usually done by measuring this ratio. So just that we focus on those two things, there's basically two isotopes here and two isotopes here that we focus on. They have the same, all three forms of carbon have 6 protons in the nucleus, but they have different masses. And this mass difference in both these cases, in this case is a factor of 2, it causes big fractionation. In this case, it's something less than 10%, it causes small fractionation. Then we go to oxygen, we got 3 isotopes, okay? 16, 17, and 18. Now we're going to learn in the, when we go into the high temperature part of the class, we start to talk about how the elements are formed in stars and in what proportion. We're going to learn that there's a big variation on Earth and in our sun and pretty much everywhere else that we're able to observe in the relative amount of even to odd mass isotopes. Odd mass isotopes are much less abundant. And so the amount of oxygen 17 that we have to start off with is way, way less than the amount of 16 or 18. There's way more 16 than 18, and we'll talk about how that forms too. Things with up to the mass of iron, things with masses of intervals of 4 end up being really the dominant thing. So oxygen 16, carbon 12, helium 4, etc. But in any event, we have these 3 isotopes. For most of the history of studying isotope geochemistry, people focus on 16 and 18 because 17 is really hard to measure. But people measure 17, and you find some really interesting things out when you have 3 isotopes that you can compare. And we'll talk a little bit about that, but not a ton. So the mass difference between oxygen 16 and 18, there's 2 AMU here, right? So the relative difference is greater than there is here, where there's only 1 AMU. So we get somewhat intermediate fractionation between hydrogen and carbon for oxygen. Right? So this is just sort of written out here. Carbon 13 is about 8% heavier than carbon 12. Oxygen 18 is about 12% heavier than oxygen 16. And as I alluded to before when I was talking about the chemistry of these things, the mass is everything for isotope fractionation. There are some other kinds of isotope fractionation that we're starting to learn about in the last decade or so that are called non-mass dependent. They have to do with other nuclear properties or things that happen mostly in the atmosphere. We're not going to talk about them. We're mostly going to focus on mass-dependent isotope fractionation, which is the dominant form of isotope fractionation. So just based on the difference in the mass between the heavy and the light isotopes of those 3 elemental systems we talked about, we expect, if we looked around materials in the hydrologic cycle, for instance, or in the carbon cycle, that we see the most fractionation between hydrogen and deuterium, because there's the most mass difference between these 2 things. Next most in this, and next most here. Now, of course, it gets more complicated than that, and there's overlap because the amount of fractionation depends on the process, but just based on the masses, this is kind of what we expect. And when we go to heavier systems, like sulfur, which is a common thing, right? Sulfur sits below oxygen in the periodic chart, we get significantly less fractionation because sulfur is about twice as heavy as oxygen. We expect to see about half as much range. Does that make sense, everyone? Okay. Yeah. It turns out that the separation of isotopes from each other depends on temperature. The reason it depends on temperature is because temperature reflects molecular motion. Not only motion of individual molecules that might be racing around, for instance, in the atmosphere, but also motion that is captured within chemical bonds, which cause bonds to vibrate more or less as a function of what the temperature is. And in both of those cases, the temperature makes the system more energetic at overall higher temperature. And at higher temperature, where the whole system is more energetic, we get less fractionation effect between heavy and light isotopes. The colder you make a system, the less net energy it has, and the easier it is to separate the proportions of masses from each other of different isotopes of the same element in a given system. So think about like you're evaporating water, for instance, from the ocean into the atmosphere. The fractionation of oxygen isotopes in that water from that process of fractionation, and we'll talk about the specifics of that in a second, but the warmer the temperature that happens at, the less fractionation you get, all other things being equal. So again, it gives us another way of trying to record paleo temperatures on the planet and other paleo conditions. So let's look at water, okay? And we're going to talk about three kinds of effects of isotope fractionation. There are other ones, especially ones that are mediated by organisms, but these are the kind of three effects that are, you know, most obvious and the first ones that were worked out. The one kind of effect has to do with the overall mass of a molecule. How big is a molecule as a function, or how heavy, I should say, as a function of the isotopes it contains. There's another effect, which has to do with if we have a chemical bond between two elements, right, and we compare two different chemical bonds, like say, for instance, hydrogen and oxygen chemical bonds between heavy and light isotopes, there's going to be different amount of vibration stored in that bond, which makes some bonds easier to break and some bonds less easy to break when we are forming and breaking bonds. So there's these two things, and then superposed on them are kinetic effects. Remember, kinetic effects are things that speed up or slow down chemical reactions as a function of the conditions that are present. And it turns out that in both of these cases, kinetic effects, if we don't let the system reach chemical equilibrium, they magnify the size of the angle. So like in the example I gave you of evaporating water, if we were to evaporate a bunch of water and give it enough time to reach chemical equilibrium, we would predict a certain fractionation factor, we call it, between the water that's in the atmosphere and the water that's in the liquid form beneath it. But if we don't let the water reach chemical equilibrium, basically starts to evaporate and maybe some winds pull it away, then we get a bigger effect than we would have gotten because the lighter isotopes reach chemical equilibrium faster than the heavier isotopes. And all of this goes back to mass. And we'll see how that goes to mass on the next few slides. But the first thing I want to talk about are these type A effects for water. So I've written out all the forms of water that include hydrogen or deuterium and oxygen-16 and oxygen-18. I've left off oxygen-17 because it's a minor isotope. We don't talk about it. I've left off tritium, minor isotope. We don't talk about it in this context. But if we look at, this is the lightest possible form of water. Hydrogen, hydrogen-1, and oxygen-16, right? So this molecule weighs 18. This is the heaviest form of water with 2 deuteriums and 1 oxygen-18. That's 22. Right, so that's a pretty significant difference. This molecule is 22% heavier than that one. We expect isotope fractionation in processes that will reflect differences in the mass of water. Evaporation is one of the things that affects mass. Okay, that reflects mass, I should say. Okay, how? Okay, so this is a relationship that tells us how fast our molecule is moving as a function of the temperature and their mass, something called the Boltzmann's constant. And this is something that's worked out. If you may have learned this in some physics classes, but you get a statistical distribution of materials that kind of have a Gaussian distribution, and the peak velocity is described by this. Right? You can imagine if you just have a bunch of gas molecules, they start out all with the same velocity and they start colliding with each other and colliding with the walls of a balloon or the room or whatever. Some of them are going to start moving a little bit faster, some of them a little bit slower. So this is kind of a simplification of what we think the mean velocity is. But the key thing here is that this is a constant and this is a constant. And so the velocity is basically proportional to the square root of the temperature over the mass. So you can think of a situation where we want to look at two different temperature conditions, maybe evaporation of water near the poles and near the equator. We're gonna, if we set the mass constant, right, we only look at one of the forms of water. The most common form in terms of abundance is this form. Okay, so we just looked at that, and we looked at how it varies as a function of temperature. We learned something about what this Boltzmann's distribution is and what the energy relationships are there. Another thing we could do is say, no, we're going to look at the same temperature, right? But we're going to look at two different types of water, right? Maybe the one with the 16, oxygen 16, or one with the oxygen 18. What's going to be different about them is their mass. So the amount of velocity difference between a water molecule of a mass of 18 and a water molecule of a mass of 22 is going to be reflected as a delta M, and that is the square root of that. And that allows us to predict exactly how much fractionation we're going to get. So for instance, if I have two water molecules or two hydrogen molecules in the example, this is for hydrogen and this is for water, right? And I write this equation twice and I put it on top of each other, right? So the equation for the heavy isotope and the equation for the light isotope, velocity 1 and velocity 2. I just take this equation, divide it by itself, all the constants drop out. And you will see that the equation relaxes down to, it's just algebra, that the ratio of the velocities is the inverse ratio of the masses to the square root. Okay. So when we do that and we put in the numbers for hydrogen and deuterium gas, H2 and D2, we find out that there's a difference of about 40%. That's a really big difference in velocity. That's the ratio of the velocity. Okay. Now, if we do that for water, the kind of heaviest water we can have, the lightest water we can have, about 10%. So what we learn is that the lighter mass isotope, the water molecule is built out of that, or hydrogen gas is built out of that, is moving a lot faster than the heavier in both cases. And that's going to help it in, for instance, processes like evaporation. So if we think about the oceans today, or a lake, or a glacier, doesn't really matter. When we evaporate water, and in the process of going from a solid right to the gas phase, we call it sublimation. That happens over glaciers. If we look at what's in the solid or liquid phase and what's in the atmosphere above it, what we're going to find is that the lighter molecules evaporate better because they're moving faster. So we get an enrichment in oxygen 16 relative to 18 whenever we evaporate water. This amount of difference depends on the temperature. The hotter the temperature, the less the difference, as I talked about a few moments ago. The colder the temperature, the bigger the difference. So if you want to think about here in Hawaii, what was happening when water was evaporating from the oceans today versus during the last ice age? During the last ice age, the water going into the atmosphere had more oxygen 16 in its water relative to 18 because it was colder back then. Not that much, but when you go to higher latitudes, that difference really shows up. And the reason for that is that this molecule is moving faster. Because it's moving faster, because it has more kinetic energy, it's able to better break the hydrogen bonds that keep water molecules together in a liquid form and to break free. Yeah. Okay. So now here's the other type of effects, which have to do with chemical bonding. In that case, water molecules were just evaporating in a bulk sense. We weren't breaking or forming any bonds. What about when we break and form bonds, which happens all the time in nature? So it turns out that quantum mechanically, the way we explain bond energy is to think about them as springs with a spring constant. Everyone had their physics class. We learned about stiff springs and not so stiff springs. Right? So a stiff spring is like a strong bond. And a less stiff spring is like a weak bond, okay? Now, bond energy, which is vibration in the spring, reflects temperature, and it reflects the mass of the two things next to it. So that whereas chemically, from a valence electron perspective, a hydrogen-oxygen bond is a hydrogen-oxygen bond regardless of which flavor of hydrogen-oxygen we have, when we look at them from the mass perspective, okay, turns out that the heavier masses make a slightly stiffer spring, a little bit harder for them to vibrate. So if they're a little bit harder for them to vibrate, a little bit harder for them to break that bond. So that processes that form and break bonds tend to favor the light isotopes when we're forming and breaking bonds. And this is described with another relationship, which is derived from the Schrodinger equation as applied to this particular case, solved for one electron in one bond, that the energy of that has this relationship, and H is another constant, it's Planck's constant. But the key thing here is that we see mass again in the square root. And so if we were to do the same thing, we're looking at how much energy is stored in a bond between a hydrogen oxygen 16 bond and a deuterium oxygen 16 bond. We can understand that difference by doing a ratio, right, of the velocity in the bond, or we can think of it from bond energy perspective. It doesn't really matter, but in both cases, that difference is going to be inversely proportional to the square root of the masses, just like it was for the kinetic energy in the example I gave before. So that tells us that the energy in the bond that's got the heavier isotope is higher. The energy in the bond that's got the lighter isotope is less. So that's kind of summarized here. And we have stronger and weaker bonds as a function of the isotope. Okay, so now imagine a situation where we take our system all the way down to hypothetical absolute zero, right? The minimum amount of vibration you can have. And the minimum amount of vibration you can have, the difference in vibration in that bond is only going to be a function of the masses. It's a theoretical value, so we never really get there. But you could, in theory, measure the velocity difference in a bond that's stretching slightly higher or lower spring constant. That gives you a specific value. Now, the energy it takes to break a bond has to do with the valence electrons. It doesn't have to do with the masses. It has to do with how much energy you have to stick into a bond to promote electrons from bonding orbitals to anti-bonding orbitals and pull them apart. So that is the same, that energy of dissociation is the same regardless of the isotope. So what's really happening here in the bond energy scenario, type B fractionation, is that the difference in mass is causing a slight difference in the amount of inherent energy stored in the bond, that if we then heat that up and get it to the dissociation limit, it takes less energy to do the light isotope bond than it does to do the heavy isotope. Okay. This is physics. Does that not make sense to everyone? You're looking like
the heavier isotope, it's easier to get it to the next orbital.
No, this is the light one, that's the heavy one. The heavy one is vibrating a little bit
Oh,
less.
okay. So you're saying that the lighter isotope is easier to
Easier to
move.
break. You got to throw in
Yeah.
a little extra increment of energy to make this one.
Oh,
because you
okay,
gotta
okay.
go up.
I heard that like complete opposite. I was like, wait, that doesn't make physically sense. I don't know.
So now you can see, well, where do we see this? Okay. So whereas that other effect, we see it all the time in the hydrologic cycle. We'll get some examples in a second of that, the evaporation of water. This one we see, for instance, when we do photosynthesis and respiration. If we take a bunch of CO2 and water and we stick it together to make algal protoplasm, right? We're kind of to break some carbon oxygen bonds, make some carbon hydrogen bonds. We're going to get some chemical fractionation. We're going to see it when we make calcium carbonate shells. We're going to see it when organic matter in the form of POC gets stored in sediments, and then later we pull them out and burn that stuff as fossil fuels, and we put that into the atmosphere. The kind of CO2 that we put into the atmosphere by burning petroleum has a different carbon isotopic composition than the CO2 that was there before. So in addition to us, changing the amount of CO2 in the atmosphere and heating up the planet, we're also changing its isotopic composition. It's not that that has any necessary manifestation for global warming, but it's another thing we can track. And we can look at times in the past when humans weren't the thing that was driving it, but maybe the way plate tectonics was operating, the way the carbon cycle was operating, caused us to have different rates of remineralization or digestion of organic matter naturally. It's going to put CO2 into the atmosphere as well and cause fluctuation. So there's a lot of different types of processes that can be investigated with this phenomenon. And unfortunately, in many cases, we have superimposed effects, right? Like if you have an upper water column in the ocean, right near the surface, and it's got some photosynthesizing organisms, and they're making some organic matter, and they're making some calcium carbonate shell, the isotopic composition of those things is going to reflect fundamentally the processes through which that formed, but also changes in the water. So if the water in that location gets hotter, so it can experience more evaporation and changes oxygen isotopic composition through evaporation, then we will have that process superimposed on our forming and breaking of bonds to make the Redfield ratio. So those two things work together, usually. Okay, so the next thing is, well, how do we quantify this? So there's a bunch of different ways of doing it, and you can do it through equilibrium considerations, which is one way of doing it, and that gives us a factor called R or alpha. There's a better way of doing it, in my opinion, a more standard way, which is to compare things to a standard material. We'll get to that in a second. But if we just think about this simple reaction, we've got some water and some hydrogen gas, right? And we got one deuterium atom in that mix. So that deuterium can either be connected to the hydrogen gas or it can be connected to the water, right? And we can write a chemical equilibrium constant for that, which we've written here. It's just the activity of the four things, right? And another way to think about that equilibrium constant is the ratio of two ratios. It is the ratio of, we cover this up and just look at this. This is the isotopic composition of hydrogen and water, the ratio of HDO to H2O. And this is the isotopic composition of hydrogen in the hydrogen gas, H2 over Hd. So I've rewritten equilibrium constant as the ratio of hydrogen in the water and the ratio of hydrogen in the hydrogen, which is called alpha. It's just a thing. You will see it. You'll see it in a moment in slides. It goes directly back from equilibrium constant. Okay. And so we can look at, for instance, we all know, we've talked about this multiple times, equilibrium constants are temperature dependent, right? So we know that when we change temperature, we're going to change this value. We can go into a lab and we can quantify this. Okay, well, how does that fractionation happen at 20 degrees, 25 degrees C, 30 degrees C, 100 degrees C? Compare it, make ourselves a little plot, and then we can go look in nature at the isotopic composition of hydrogen and water in a place where we think that that's the main process that's going on. And we can say something about what was the temperature, just by the relationship of alpha with temperature, which is something we can predict really easily because of the Gibbs free energy relationship to temperature. And remember, delta G naught equals minus RT natural log of K, right? So there's a direct linear relationship between equilibrium and Gibbs free energy. And we know how that is related to temperature. There's a pretty strong theory here that we can use. And so, for instance, this is just an example. If we now look at the evaporation of water, right? So we've got some oxygen 16 enriched water, and some oxygen 18 enriched water in the liquid and in the vapor state, and they're going to evaporate and reach some kind of equilibrium. As we've just talked about, this is one of these type A fractionations. In the vapor phase, we're going to get more of this stuff than this. And in the water that's left behind, we're going to have more of this than this. That's just how the fractionation kind of works its way out. We already know about we already looked at the masses and so forth, but when we measure this ratio of ratios, which is the isotopic composition of water in the liquid and the isotopic composition of water in the vapor, that ratio is 1.0092 at 25 degrees C. That means that all the things being equal at room temperature, we let this evaporation happen, the isotopes are going to be about 1% heavier in the liquid than they are in the water. That's just like a measurement. Okay. So this kind of measurement, this alpha, is useful in a laboratory setting and in some very specific cases where we parameterize things for a bunch of temperatures. But more often than not, because we are comparing across environments where more than temperature is varying, right? It's not just one variable, it's a ton of stuff there. Instead, what we tend to do is compare the ratio to a standard material. For instance, there's something called standard mean ocean water. It's not actually a mean of ocean water, but it's a value that originally there was a vat of this stuff in the lab where I was a grad student. That's just all been used up, but they made artificial stuff. Since then, that was like a mixture of ocean water collected in a bunch of different places, stuck together in a vat and said, okay, this is the average. And then you can basically compare stuff to that. This is like something that was happening in the 60s and 70s when they first made that average. So you can say, all right, here's a place where our water is heavier than the average. Here's a place where our water is lighter than the average, or a lot lighter, or a lot heavier, or whatever. And the way that's done is by taking the ratio, again, one of these ratios, and comparing to that same ratio in a standard. So for instance, oxygen 18:16 ratio in water that you collected somewhere, rainwater in Hawaii, for instance, and compare it to the standard. For instance, standard mean ocean water. And subtract it from 1, okay? And that is one kind of factor that is called a delta, okay? You can also write the same equation this way, RA minus standard over R standard. These are mathematically equivalent to each other. We're really looking at the fractional deviation of our material relative to a standard. And when this value is 0, then our material has the same isotopic composition as the standard. Okay? When it's the same, this ratio becomes 1, 1 minus 1 is 0. I have everyone with me? Okay. So there's some values of that standard for three elements that we're talking about. So for hydrogen, it's pretty much always compared to something called SMO, standard mean ocean water, which has a value. It doesn't even matter what its absolute value is, but it's got a value. And when we go all around the hydrologic cycle, we take water from different places, glaciers, rivers, rainwater, ocean water, okay, we find a variation in that ratio, the difference between the standard and what we've actually measured. It goes anywhere from minus 400-ish to plus 50. It's a pretty big range. Okay. If we look at rocks and minerals, take the basalts, here that were formed and have been weathered in the presence of water. Again, we're making clay minerals, we're forming and breaking bonds, we're exchanging isotopes. We have a pretty big variation. There isn't much hydrogen in the rocks, right? But think about all the OHs and the clays. There's a lot of hydrogen. So we can get some isotopic fractionation. It's less in the rocks than it is in the water. We look at oxygen. Oxygen can be compared to the SMO scale. And we do that when we're looking at water. Okay. And so the variations, they're not as big because the mass differences between oxygen 16 and 18 aren't as big as they are between the hydrogen isotopes. And so you can see the corresponding variations in natural waters and in rocks. Now, sometimes it is not convenient to compare the isotopes to SMO. You can do it, but you get kind of funny numbers. And those cases are when we're looking at the isotopes in shell material. So instead, we use a different standard called PDB, which stands for the PD belemnite. It's a particular shell that comes, I think, from North Carolina or South Carolina or something that, again, someone decided way back on, hey man, this would make a good standard. I got a bunch of it. Let's grind it up and make a powder and give it to everyone in the world. Everyone agrees on a value for this. They agree on a value for that. And then they measure the value in their particular sample and they come up with, ranges. And so what you can see is for the exact same materials, the range of the isotopic fractionation for oxygen is, higher numbers relative to SMO than it is PDB. And this is because of the nature of the two materials themselves. And so you can also see that for carbon isotopes, that one tends to only be measured against its PDB. So if you're looking at carbon and oxygen isotopes in calcium carbonate marine sediments, you're probably going to do your carbon and your oxygen on the PDB scale. If you're looking at oxygen and hydrogen in the hydrologic cycle in water, you're probably going to do your oxygen and hydrogen on the SMO scale, if that makes sense. You could do either, and there's just a simple algebraic expression that can convert oxygen isotopic composition from SMO to PDB, right? In some years, I make you do this in a homework assignment. It's not hard. I don't know. It seems not hard when I assign it, but it is just a relationship. Okay. So isotope standards have a second benefit, which is to say, all right, we got 500 labs in the world making these measurements. Are you guys all making your measurements the same? Are you as good at making measurements? How much variation do you get out of your mass spectrometer? How is grad student A, and grad student B, and technician C, how good are they at making measurements? Because all those things matter. And so every time you write a paper where you talk about isotopic compositions, you also publish repeat measurements of your standard. And that will tell you something about your precision and your accuracy and everything else. And for a long time in isotope geochemistry, people weren't doing this. We have people publishing papers and they'd say, oh, look, I'm finding the isotopic composition of the carbon in this area is this. And someone else would, oh, that's weird. I got this thing over here and they don't match up. And then later people would go and say, well, measure the standard. And then we get different numbers on the standard. So we normalize to the standard. It turns out that when you're making these measurements, in addition to the natural processes that cause isotope fractionation, when you start to prepare a sample in the lab, you can also cause isotope fractionation. If you don't completely dissolve something, or when you're trying to put it into your mass spectrometer, 100% of it doesn't go in, and there's a whole myriad of other processes as well, you can induce fractionation. So you put your standard through the same process and see, well, how much fractionation am I adding? And you work it out so that you can minimize the sources of uncertainty and differences, biases, we call them, between different laboratories to get back to a more realistic assessment of what's the actual inherent isotope variation. So standards are useful for both of these methods, and they're kind of a critical aspect of analytical geochemistry. Okay, so when we take this ratio and we look at it in most materials, we find out that they are relatively small numbers. Percent, 10th of percent, sometimes 10%. So we often have to multiply them by 1,000. And what that does is take a number that would be, instead of being 0.001, it becomes 1. So when you look in tables, they are usually in delta notation. Delta notation means deviations in parts per 1,000. That's what delta means, which is basically the same equation we talked about before, multiplied by 1,000. I've got the two forms here. So here's like this one, like I don't have very many pet peeves in life, but here's one of them. You can always tell the difference between a geologist who doesn't know geochemistry and a geochemist, because a geologist will refer to this as a del. It's a del 18, like Del Taco, or one of these. It's just like, it's not correct. It's a delta, not a del. So please, if you're ever, you can show how educated you are by always referring to it as a delta and not a del. So here's some other relationships. Remember that alpha we talked about, right? Which is, it comes from the equilibrium constant. This is how alpha relates to the delta of the two materials that were equilibrating with each other. So it's just, again, it's a chemical transformation, and basically that you take each of the deltas and you add 1,000 to it, and then you divide them by each other. Okay, and this is a slight approximation of what that is. If we take two deltas, the delta of oxygen 18 in water in the atmosphere and water in liquid water, for instance, and we subtract them from each other, it gives us a capital delta. You're like, why do we want that? Well, it turns out that a lot of the temperature parameterizations are done in this unit. Okay, so the difference between the small deltas is sometimes called a big delta. That's just the capital Greek letter delta, it's a triangle. And that is approximately equal to 1,000 times the natural log of the alpha. And that goes all the way back to, you have to do the math for yourself, but that goes back to the delta G equals minus RT log K. That's where the natural log comes in from. Because alpha is basically an equilibrium constant K. Okay, so here's a nice topic exchange that is relevant to what we were talking about last time in the first part today, which is we're looking at the carbon cycle. We're looking at some CO2, it's in the atmosphere and it dissolves into water, right? And during that process, we get some exchange between the isotopic composition of oxygen and the CO2 and oxygen in the water. Right? And so you can see here, I've moved the oxygen 18 around. So that's going to affect what is the oxygen isotopic composition of bicarbonate ions in the ocean. Now you got some photosynthesizing organisms like, hey man, I'm going to make a shell. I'm going to make some calcium carbonate. Okay, my calcium carbonate that I make is going to reflect a bunch of stuff like the enzymatic processes that go on in that organism to make shells in the first place. We call those vital effects. We'll get to them later. But it's also just the chemical equilibrium of, all right, I'm growing as an organism and I'm making a shell. What is the oxygen isotopic composition of the bicarbonate in the water that I'm growing from? If that's different, then the net result of what's going to be the isotopic combination of the carbon, oxygen and the carbon is going to be different. Right? So you can put these two things together into a single reaction. You can write a relationship that basically says, all right, how does the calcium carbonate, the oxidized isotopic composition of oxygen in calcium carbonate relate to the water that it grew in? And this is another one of these paleo proxies. If you recall, last time I showed you that plot with the variation in oxygen isotopic composition of calcium carbonate in benthic foram shells between the glacial and interglacial cycles. That's a measure of this, and it's largely used to tell us something about this, to infer this, which tells us something about how the hydrologic cycle was operating back into the past. Okay? So that's kind of important, and we'll see this come back up soon. So the sort of last thing I kind of want to talk about is the temperature dependence of isotopic fractionation. This is the relationship of the change, the partial differential of equilibrium constant with respect to temperature staying at constant pressure, and how it's expressed in enthalpy units. I've rewritten it with alpha units and so forth. But what you see here is that it is essentially proportional to 1 over temperature squared. So when people try to infer the temperature effect on fractionation, they do what's called parameterization. We measure the system at a bunch of different temperatures, then we do a line fit to it using the functional form that we expect the equilibrium constant to vary as a function of temperature, which means over T squared. So sometimes you'll see plots of that big delta, which is the difference between the little deltas, which if you recall was 1,000 natural log of the alpha being the equilibrium constant, these being the ratios of isotopic composition in the materials times 1,000, that they are parameterized by, you make these measurements, you look at the actual values, and they fit a line, and the line will have the form of either, some constant over temperature squared, or sometimes it's a value A times 10 to the minus 6 because it's a small value plus B. And it's just different systems require slightly different parameterizations. So these are experimentally determined, and here's some examples of that. So you can see down here in the noise, this is 10 to the 6 times temperature to the minus 2 in units of Kelvin, right? So that's 1 over T squared times a million, because the units are really small. They just want to blow it up to make it easier to see. This is 1,000 natural log of alpha, which, as the diagram says here, that is delta, or that is the difference between the little deltas. This is the variation in oxygen isotopic composition of a bunch of different minerals that are interacting with water as a function of temperature. Anorthite, muscovite, feldspar, quartz, okay? So since this is 1 over T squared, this is low temperature, high temperature, right? And so we can see much more fractionation when we form quartz in equilibrium with water at lower temperature. Just as I sort of said before, as the temperature increases, the fractionation gets different. So again, you could go into a system, let's say you're thinking about, you know that certain minerals like gold mineralization in a vein that's got a lot of silica in it is favored at a certain temperature. You can go and prospect all around, pick up a bunch of quartz and measure its oxygen isotopic composition and say, oh yes, these are the ones that are at a good temperature. These are the ones that are at a bad temperature. There's all sorts of applications. This is how the same exact data looks when we plot it versus temperature. Okay, they have this kind of exponential looking patterns. Okay, so the temperature dependence of fractionation is a real thing. And this just shows you, for instance, experimentally determined temperature dependence without biological effects, without viral effects, of fractionation of oxygen isotopes in calcium carbonate when an organism grows in seawater, a foraminifera, to make a shell. This is the equation for it on the SMO scale, and this is the equation for it on the PDB scale. They have slightly different constants. They're not that different, but someone went and measured, they drew a bunch of forams, and they said, yep, I'm going to fit a curve, and this is how it varies as a function of temperature, right? And we have these for all sorts of different situations and scenarios that people can use to reconstruct paleo temperatures from oxygen isotopic composition. So there's just a few slides here that show you some materials on Earth and what their isotopic compositions are. this is the hydrogen isotopic composition of the full hydrologic cycle as expressed as atmospheric water. Ocean water has a small variation. So as you can imagine, when we evaporate water from the oceans, we put it in the atmosphere, that's going to depend on where it happens, like near the poles, near the equator, you know, et cetera, et cetera. We get a big variation here, and a small variation here, because there's a big mass of seawater. So we want to take a little bit of water out and put it in the atmosphere. It doesn't really change the ocean very much, but it changes the atmosphere a lot. And we see this recorded. We can look at the water that gets into the atmosphere that then eventually gets transported and shows up in the glaciers. That changes over time as a hydrogen isotopic composition. It tells us something about average temperatures on the planet. And this is a big thing in temperature reconstruction. And you can see here sedimentary rocks, igneous rocks, lower crustal rocks, meteorites. You know, the relevance of this will become important later in the semester. But in essence, as the temperature of the system goes up, the variation goes down in the rock. Now, this is a similar thing for oxygen isotopic composition here. Again, the hydrologic cycle, freshwater, huge variation, seawater, small variation, different kinds of rocks, the temperature of the system, as it goes up, the variation goes down. And this is for carbon, okay? And this is now, you gotta look carefully, this is carbon on the PDB scale. PDB is a shell, right? And so we're comparing relative to that. And so we see marine carbonates are up here. They're pretty close to zero, right? Because PDB is also marine carbonate. Everything else is lighter than that. Okay. So that especially when we go into atmospheric bicarbonate or CO2 in the atmosphere, or living organisms, or non-marine organisms, things that live on the land masses, coal, marine petroleum. And you can actually see the difference between coal and marine petroleum reflect the difference between land plants and non-marine plants and marine plants. And again, the variations are bigger on this end of the scale. So the very last few slides, I think I want to pick up next time. But the last thing that's part of this topic before we then go on to try and use this for paleoclimate reconstruction is to think a little bit about how these variations manifest themselves as we look at the hydrologic cycle and how it reflects temperature patterns today and how it would reflect in the past. And this slide just summarizes kind of what I just told you about this stuff. But I'm going to leave it there, ask you if you have any questions, and then we'll pick up this conversation next week. Anyone have any questions? Yeah.
I have one question. So for the quantifying isotropic fractionation part where you talked about, or wait, I think it's that part. Maybe it was the part before.
With the R's, the alphas, or
Alphas and the deltas.
this one?
Yeah, so this slide right here. So this is, so delta is equal to this, right?
Yes. delta
Okay,
is
but
equal to-
then why, so in this alpha, I guess, equation, like why, okay, so you're multiplying by 1,000 here, wouldn't the thousands cancel out and then the one plus, or the plus one and the minus one cancel out? So then wouldn't it just be this? Like, wouldn't it just be easier to like,
You just have to do the algebra yourself. It's basically, it might actually be easier to think about it using this equation, but the part of this that doesn't cancel out is the one part, right? So if you put this equation and you subtract it from another, you will see that because
it like, okay, so for example, if you were to take this and put this over one or over 1,000, the thousands cancel out. So then you have this minus one, and then it would be one plus this